Uh, I'm going to start just by talking about Beer's law, which I hope is at least somewhat familiar, maybe to most of you, depending on the amount of chemistry class and stuff you've had before. There's a nice footnote in the Mobley textbook on page 357. If you would like to get into the history of like who did what, this is sometimes called the Beer-Lambert-Bourgeois law. Bourgeois and Lambert found that light decays, or first described that light decays exponentially through a medium, right? So as you have light that goes into a fluid medium, and if its properties are all the same, it's going to decay with some exponential decay coefficient. So in the equation that I've put up here, we're using L as capital L is the symbol for radiance, R the path length or the distance through the medium, and then A is our absorption coefficient. Beer further described that decay coefficient, A, is proportional to the concentration of whatever is doing the absorbing in the medium. So here, defining A as the product of A star, so the concentration specific absorption coefficient, times C, the concentration of the stuff, whatever the stuff is. So these are kind of the two important tenets, right? Exponential decay of light absorption proportional to concentration, which is what allows us to use ocean color to tell us anything about the ocean. And if there's multiple absorbing substances, Beer's law says that we can simply sum them up. So we expect there to be kind of a linear dependence of absorption on the concentrations of all of the absorbing things. Okay, I'll wait till pencils kind of stop moving. And this is, yeah, you might encounter this like in an undergraduate analytical chemistry course or something, maybe some other courses too. That's where I encountered it, I think. All right. So we can derive this. The figure that I'm showing you here is also from the Mobley textbook, and I'm going to animate some pieces of it in and out. Can you see this gray box, or is that very difficult to see? You can see the gray box, then I'm going to keep the lights on because we've been here for a long time, and I feel like it might help. I've been here a long time. So this gray box symbolizes our volume of water, and it has a thickness delta R, right? Using R as the path length of light through the water. And the capital phi here is being used as the symbol for light. So phi sub I is our incident radiance that's going into the volume. Then some of the light is absorbed, phi sub A. And what comes out in the same direction on the other side is phi sub T, the transmitted light. And then there's a little arrow going off up and to the right, and that is phi sub S. So that's the light that's been scattered within that volume. You'll notice that the phi sub S arrow has a little circle, it has a little volume indicated, and a delta omega. So that's actually the solid angle subtended by the scattering. And then we have the angle of the scattering, psi, little pitchfork Greek symbol thing. And all of our parameters are all a function of wavelength. Okay, so this is sort of our basic diagram illustrating how our IOPs work. And I think we'll come back to versions of this multiple times. So by conservation of energy, the amount of light absorbed plus the amount of light scattered plus the amount of light transmitted equals the amount of light that went in. For now, we will ignore scattering because we're only talking about absorption. Sorry, Wayne. We'll bring it back towards the end, and then we'll like really bring it back tomorrow, I know. Okay, so for now, assume there's no scattering. So conservation of energy, we just have to take account of our incident light and our transmitted light. So VA equals VI minus VT. Okay, so we define this absorption coefficient as the fractional radiance loss, which would be incident light minus transmitted light over incident light, right? That's our fractional loss across that volume. So we define absorption, fractional radiant loss per unit distance through the volume. So fractional radiant loss is inside the parentheses. So, and it's a loss, so it's minus delta VI minus VT over VI divided by delta R, the path length. And then I'm just going to use the shorthand, d phi over d phi as that fractional loss divided by dr. Okay, so that's our defining our absorption coefficient. And we can rearrange it as I've done here and put the dr with the a and the minus d phi over phi on the right-hand side. And then we can integrate both sides with respect to the path length, with respect to r. And doing that, if you've forgotten how to integrate, sometimes it's good to relearn every now and then because it makes you feel good. So you should do it. So we can integrate both sides with respect to r and plug in our limits of integration, which I've done down here. So absorption times r minus 0 on either side of our volume equals minus log of phi at the r side minus log of phi at the 0 side. Okay, and then we remember that when we simplify and substitute, so our at the r side, phi is dt, and at the 0 side, phi is phi I. So we sub those in, and then we say, we've got log of something minus log of something else, and they're the same base. So we can do that and make them log of phi t over phi I, negative. And we'll rearrange again, solve for a. And that's our equation there. And we can rearrange it as well and get to our familiar, hopefully more familiar form of Beer's law. Phi t, the light coming out, equals phi I, the light that went in, times e to the minus ar. Okay. So that's our derivation of Beer's law. We won't do that again. Unless you want me to. You want me to go back and do it again? No, we're good. Okay. Moving on. Okay, so we just derived the absorption coefficient. And that's got units of inverse meters, right? Because the numerator is unitless, log phi over phi, and the denominator has units of meters. So it's inverse meters. Spectrophotometers, so we're going to use one this afternoon. Not AC meters are also spectrophotometers, but they just give you absorption coefficients. But classical benchtop chemistry spectrophotometer will typically give you absorbance, which we symbolize with capital A rather than lowercase a. And that's defined as minus log 10, because chemists like to be difficult that way, of log or phi t over phi I. So what are the units of absorbance? Compare it to absorption coefficient. What is it missing? There's no R, right? This has no units. Light, divide by light, no units, log of that. So it's unitless. Sometimes A is also called optical density, by the way. You'll see that in older literature. Same thing. Okay, so A, absorbance, is unitless. So if we want to convert between absorption coefficient and absorbance, we need to know the path length that we made our absorbance measurement in, the length of the cuvette typically. And if we know that, then we can convert between them. We need to do a change of base to go from log base 10 to the natural log. That's a factor of 2.303. And then we have to divide by R. So that's our formula. Little a absorption coefficient is 2.303 times big A absorbance over R. Okay. Question? No, good. Okay. Okay. I did this thing where I said, we're just going to ignore scattering. You can't actually do that. We're going to measure real samples with real instruments, and there might be some scattering, and we have to figure out how to deal with it. Option 1 to deal with this is to remove the scatterers from the sample, and that is in fact what we're going to do this afternoon. Alexander has, or shortly will, filtered the samples, and then there will not be anything scattering, we hope, in them. That's going to simplify things today so that we can just learn our instruments and how to care for them and operate them. But beginning tomorrow, we will no longer be doing that. So I'm going to talk through some of the theory behind that. Yeah, Raphael. There's still, oh yeah, so there is still some scattering, but it's like molecular scattering. Yeah, so you're right. There is some scattering. We're going to remove the major, like the scatterers that are going to like really cause us problems, we will take them out by filtering.
We always forget the fundamental ingredient.
Yeah. The water is always there. And in fact, we will measure the water today. Like we'll take out all the particles. We're going to measure pure as we can get here on campus, pure water, different temperatures, different salinities. And then we'll measure some environmental water with the particles taken out, and we'll compare everything. So we will look at the water itself. Very good point. There is always scattering, but it's not very much across 1 centimeter or 10 centimeters. Yeah. Okay. So that's option 1. Option 2, to make real measurements with real instruments, real samples with real instruments, is to collect nearly all of the scattered light, right? Use a device that allows us to actually collect it and measure a fraction of it, so that then we can, by difference, figure out what the absorption was. Okay, so that's an option 2. And option 3 is to make some well-justified assumptions about the light that was scattered and apply a correction. Okay, we're gonna, so option 1, we're doing this afternoon. Options 2 and 3, there's kind of a continuum of things you do here. And that will be the lab tomorrow afternoon. And we're actually, we're gonna get all the lectures about scattering and beam attenuation tomorrow morning. So you will have more of a theoretical understanding of how the caveats of these various methods. But I'm just going to talk through them so you know the big picture for the different techniques that are available. Okay, so if the scattering is negligible, if we have taken the particles out of the water, it is negligible, not gone, because there's molecular scattering. We can use a benchtop spectrophotometer for that. These come in double beam and single beam configurations. This is a schematic showing a double beam spectrophotometer. The source is back here in the back, and it gets bounced around through some mirrors and then comes in and goes through a beam splitter. And now there's 2 beams coming into 2 parallel light paths inside the instrument that I've made arrows here for. One of them is for the sample, and one of them is for a reference material that we compare to the sample. So you measure the transmitted light through both, and then you can determine the absorbance and then the absorption coefficient of your sample. So the reference is important, right? If we're measuring CDOM absorption in an estuary, for instance, we could use pure water as our reference and look at the difference in transmission between them. Or we could measure salt water at the same salinity as our reference. We could measure water, like we should think about the temperature, right, of our reference. Our reference should be the same temperature as our sample, or we might see some of those delta T absorption effects in there. So it's important to think about what your reference should be. We might try and measure some extracted pigments in acetone and methanol for fun later this afternoon too. And in that case, we probably want to put methanol and acetone as our reference, right? So you want to match your reference. And then, yeah, you compute the sample absorption by difference. So absorbance, sample minus absorbance reference, which is minus log 10 of the transmitted light by the sample divided by the transmitted light by the reference. And our instrument will do that for us automatically. So we'll get a core. That benchtop spectrophotometer example, remember that we've got absorbance, which does not contain the path length in its definition. But we know that the absorption coefficient is a function of path length. So if we change the path length, how will that spectrophotometer's measurement of absorbance change? Like if we measure a sample in a 1 centimeter cuvette, and then we take that same sample and we measure it in a cuvette that has a path length of 10 centimeters, how will absorbance change in that case?
Nothing changed.
It won't change. We've got it. The distance delta R of 1 centimeter, more or less, shine a light through. And then you take the same water and you fill up a path of 10 centimeters and shine a light through. light decays exponentially across the volume, right? So we should have,
Increased by a factor of 10.
it'll increase, not necessarily by a factor of 10, but you should see an increase, right? In, I guess, of absorbance, yeah. Absorption. No. Yeah. We have access to, not here, but in general, you can buy cuvettes in a giant range of path lengths. All the way from teeny tiny little micro path length, 1 millimeter cuvette. I don't even know what you would be measuring in like the natural waters selection that you would need a 1 millimeter path cuvette, but they exist. All the way to 10 centimeters for a spectrophotometer. Rule of thumb is we want to try and get absorbance when we're making our measurements to fall within a range of around 0.1 to 0.4. If we start to get absorbances much larger than 0.4, we're not letting enough light through the cuvette to be detected to get a good measurement of absorbance. And so you should shorten the path length if you start to get too large of an absorbance. You'll be able to explore this with 2 cuvette path lengths and a spectrophotometer today, and then you'll also be making measurements in an AC meter at a 25 centimeter path length. So you'll be able to make those comparisons quite nicely, I think. If you are trying to measure the CDOM absorption like in the oligotrophic ocean, then 10 centimeters is not going to be enough. And really getting a cuvette much longer than that is pretty impractical. And so there's also things called liquid core waveguides or waveguide capillary cell, which is a long fiber optic tube with a flow path through the middle of it. And so you can inject a small volume sample through that and then measure the absorbance along a very long path length. These come in path lengths of 0.5 meter or even longer. They're a little finicky to use. They're sensitive to bubbles. You have to clean them really well. You know, you don't want to have particles in them. So that's it's an art. It's important when we want to try and validate absorption coefficients out in the open ocean. Okay. Another thing we can do, and this is sort of stepping beyond the remove the particles solution, but if we want to actually measure the particles, one way to do it is to put that scattering, so a sample that's absorbing but also scattering can be placed inside an integrating sphere, which is, this is my cartoon version of it, a white sphere that the sample goes in the middle of, or it can go at the entrance or the exit to it. But it's coated on the inside by a very highly reflecting material. Spectralon is the most common. And the light comes in through a port, interacts with the sample, and then some of that will be absorbed by the sample. But anything that's not absorbed by the sample then is going to pass through. If it gets scattered, fine. It's all just going to bounce around inside this spectralon coated sphere. And then you just have a little detector at the bottom. That's the detector that will collect a fraction of that. And then you know what solid angle you're looking into in the sphere, and you can back calculate how much light was there. Your software does that for you. So that's the integrating sphere approach is one way to go. Yes.
I have a question. If we were to measure the absorption spectrum of eelgrass leaf inside an integrated sphere, so the absorbance will be dependent on the area of the leaf, I guess?
So if I were going to measure eelgrass inside an integrating sphere, I would try to make a sample that is pretty small, right? That the light would interact with, but not like, I wouldn't like stuff the integrating sphere full of eelgrass.
Well,
I guess it depends on how the light's set up. So
okay, to avoid multiple scattering, like it bounces off the spectral and
yeah,
to the leaf.
So multiple scattering within the first strike of light on the sample is something to be avoided. Usually, so the integrating sphere we'll use in lab tomorrow it's in double beam configuration. So there's a port where light comes in, strikes the sample, and there's another port where light comes in and misses the sample. And so you compare the light that went through the sample once to the light that didn't go through the sample on the first strike, but then it bounces around and then it can go through the sample on subsequent strikes. And so that's how you do it. Yeah. But it's important that the first strike be free of multiple scattering. I don't know enough about eelgrass to know whether you'd worry about that in an eelgrass leaf. I would guess not, but I'm not sure. Yeah, I don't know if we have any eelgrass experts in the room. Okay. So that's the general principle of how an integrating sphere works. The path length traveled by the light, I guess I kind of spoiled that by answering your question, but the path length we want to think about is the path length of the light through the sample the first time it hits it. Subsequent times, we can back out the effect of that. And so what we're actually measuring then is the absorbed light is the incident light minus the scattered plus the transmitted light, because the integrating sphere collects both of those terms inside the parentheses, and we measure it. There are several commercial,
Sorry,
Yeah.
that's the question. So when you're using like an integrating sphere and you're measuring a sample on like a paper filter, what's the path length then
through the filter.
through a filter? Is it
Yeah, so there's path length amplification in the filter.
Okay.
There's a slide on this coming up. Can you wait?
yeah?
Okay.
sure.
All right. So for integrating spheres, the one we'll use here is a benchtop model that connects to a spectrophotometer, but there's also several commercially available options that you can use in situ or flow through. Cyperago's in situ. Yeah. Wayne invented one of them. So these are all options for, and they all have different, modes of operation, like where the light is, where the sampling port is, whether you fill the whole sphere up with sample or just a tube with the sample, and how you clean them becomes very important. What is the inside coating material for the ones that actually interact with sample?
Some variation of spectral or spectral-like material.
But coated with something so that it.
No.
Oh, really?
Yeah, so it's like cleaning becomes a major issue.
Yeah. So, yeah, the one we'll use in lab, not meant to come in contact with the sample. In fact, we will try very, very hard to keep sample from touching the inside of the sphere. Okay. Okay, so we can use an integrating sphere. We can to collect nearly all the light and measure part of it. And then we can also make well-justified assumptions about the scattered light and apply a correction. And this is kind of what's done in a class of sensors called AC meters. The well-justified assumptions also apply to filter pads. So we'll do that first. So if we are using a filter pad measurement, we want to ideally use an integrating sphere to make that measurement. So filter a sample onto a glass fiber filter, calculate the volume and how that's been condensed into the area of the filter. And then that filter goes, it goes ideally inside the spectrophotometer, which is panel D of the figure here, but you can also do this without an integrating sphere, or you can place it at the transmittance port or the reflectance port of the integrating sphere. And so then the center mode is what we'll do in lab tomorrow, but we'll put the filter pad in the middle. And so the light that goes into the filter and gets scattered, which is most of it, right? A little bit gets absorbed on the first strike, but not much. The rest of it gets scattered. We're going to account for that by collecting it with the integrating sphere. And for our reference measurement, we'll take an empty filter, just moistened with water, and measure the absorbance, apparent absorbance of that, right? So we're going to account for, using that, any of the light that might get scattered back out through the entrance port, which happens as well. And so that's our blank scans, right? So we'll have a blank filter that will measure relative to the sample filter. And this is your question. Is it simply sufficient to just subtract the absorbance of the mostly scattering empty filter? And you kind of spoiled it a little bit, but it's okay. Because that light that passes through the filter, it multiply scatters, right? The path length of light going through the filter is not just light going through the thickness of the filter. It actually bounces around in there. And so it has a longer path length with which to interact with phytoplankton particles or other particles that might be stuck in there. So we need to do an additional correction to account for the fact that light bounces around multiple times inside the filter. So there's the way that the field has come up with to do this is to make a bunch of paired measurements of samples that are filtered onto filter pads, and then compare them to the same sample in a cuvette. And the cuvette is actually suspended in the middle of the integrating sphere, right? So there is no filter pad. Ideally, your sample has to not be multiply scattering in a 1 centimeter cuvette, which is usually okay. And then you compare that to the filter pad version and come up with an empirical function that relates with the filter pad to no filter pad. And so it accounts for the amount of path length amplification within the filter pad. It depends on where the filter is in the sphere. So if you have it at the entrance or the exit versus in the middle, you're going to use a different empirical function to correct for the fact that there's multiple scattering in there. The two figures on the, so the T method up here is if you just put the filter at the entrance. The TR method is if you take the same filter, you measure it here and you measure it here. And then the IS method is putting the filter inside the sphere. So these are kind of these relationships between absorbance in suspension, OD sub S on the y-axis of each figure. And then ODF is the optical density of the filter by all of these different methods. That's on the horizontal axis. And so you can see that there's a bunch of different studies that kind of tried to do this. The lower right-hand corner one is the one where you need the least correction, right? And this is the method that we'll be using here. But there's other options to try and correct for that. Okay, I'm going to stop here. Questions about integrating spheres, filter pad measurements. This will be lab tomorrow. Yes.
On these figures with the integrating spheres, so I'm seeing the detector for the scattering, but then there's also a detector opposite the incoming light, correct?
No. So this one, panel A is no integrating sphere. So this is just, we just stick the filter in a regular spectrophotometer without one. And that's actually hard. That's not doesn't give you as accurate a result. All of the others, the detector is orthogonal to the incoming light. So there is no detector facing the light. Yeah. So you're subsampling part of the light by looking orthogonally to it, right? You're only seeing what's bounced all around, been integrated, if you will, by the integrating sphere. Yeah. That we'll look at 1 and 2. Can like peer inside and see the detector down there. Yeah. Okay. Okay.
This afternoon, we're just using spectrophotometers.
Right now, so I'm talking through theory for tomorrow. Yeah, today we're just no scatterers. We filtered, well, few scatterers. We filtered the water.
The entire measurement is made based off of the light that's scattered and not actually by perceiving the filter. Is that what you're getting at?
Yeah.
Okay.
Yeah.
Because of the orthogonal receiver, whatever.
Yeah, the detector is like looking up.
Right.
Yeah. It's actually baffled in a weird way too.
I use an integrating sphere a lot, and I've never really like thought of it.
Yeah.
So much sense.
Yeah.
Is there a difference in the uncertainties for each of these methods?
Yeah. So the one without the integrating sphere has the highest, just relative, right? Highest uncertainty. You have a little bit of improvement by just measuring the filter at the entrance port because you're still losing all the light that's scattered to the side. If you measure it both at the entrance and at the exit, that's a substantial improvement, but it takes 2 measurements. And in both cases, you're losing some light. inside the integrating sphere is generally thought to be the most accurate or most precise way.
What about for the kind of other two options we had?
The
So if we don't have an integrating sphere
at all.
at all,
Yeah. Can I bounce that one to Ivana? You've never done
I
it.
found that 1995 Oceanoptics class website, I'm sharing. it. So we are listening.
The question is making filter pad measurements without an integrating sphere, which I have never done. Yes.
I mean, you don't, it kind of, it's the issue with the scattering stuff. There's
Yeah.
like, it's so hard to correct it. With the correction that you're doing, you're following some kind of model assumptions and they're never as good as the integrating sphere. I will stop there and not talk more about it. I think I would refer that to Sasha because she has done that much more than I have.
Yeah. We'll be here this
However,
afternoon.
I have in the handout tomorrow for the afternoon class, there's a link to the ISCCG report. That was written like, I don't know, like 5-6 years ago. Yeah, that's the one. And in there, there's so much information. In theory, I think I was second year of grad school, when I decided that ACS is my instrument. And that was it. So, but it's just like you can't account for all the, the scattering and lost life, and that's, it's really the corrections are that much harder, you make much more assumptions. Is that a good answer? Not really.
I mean,
That's not possible, but I would really
Yeah.
like, push you towards Sasha.
Yeah.
Because I think she was part of the call, but they did some kind of comparisons.
Be here at 3:30.
yeah, she'll come to lab this afternoon.
As soon as she comes, just ask her. Right.
Yeah. Sasha, why weren't you here earlier? We had all these questions.
I can measure. Second year of grad school, that's a long time.
Maybe this lab tomorrow will also decide you against measuring filter band absorption. Who knows?
Also on the IFCCG, which will come up a lot, if you're not familiar, is the International Ocean Color Coordinating Group. And they have amazing reports, they put a lot of stuff together. I guess something I went to the summer lecture series from IFCCG, anyway, so here I mentioned that acronym.
And usually when we say ISCCG report, it's referring to, a standard protocol that we follow to measure certain things. It doesn't usually community developed protocols. It's not like, the one that says this way and the door Max says, no. There's a group of people that are really, really good in that stuff. And you'll notice that my name is not in protocols. And and then they come together and they're really, really saying you do some comparisons and stuff like that and publish these things that we usually follow. You should follow. This is stuff that the methods that we're teaching you here, following these ISCCG.
I would
Yes.
ask a question. Is it correct to think of an integrating sphere as just a trap for light, where
Yeah.
everything that comes in will eventually bounce back to the detector?
Yeah,
That is the goal.
That's the thing.
It's not perfect.
It's not perfect, yeah, right?
Yeah.
but it's perfect
But
than
it's-
swapping,
Yeah.
and
Oh, yeah.
filter pad and stuff, but you don't have that stuff, so there's lots of light loss, but it's not reabsorbed back, so that scattering correction is really hard, you making lots of assumptions.
Yes.
But the scattering correction, I mean, for the multiple scattering, it was in a good way also when the field is very loaded, like into bit condition, high to bit condition, there is a certain point that, I mean.
You don't
if,
want
the
too
data
much.
gets affected by
Yeah.
any way, it can be.
Yes.
So it's not good always.
Yeah, so that the volume of material that's put onto the filter needs to be the right amount to get your optical density into that range, that 0.1 to 0.4 range that you want, even per filter pad in an integrating sphere. And we're actually going to do you guys will do this. You'll test the effect of loading the filter too much or underloading it tomorrow in lab, so you can see the effect of that.
Thank you.
Yes.
My question is there a significance of like that window of numbers like 0.1 to 0.4 and what you possible? Because you said like it would be wrong to start adding values higher than that
Right.
0.4. So like what is the significance of like
Right.
those values?
So if you take an absorbance of 0.4, and actually, I don't want to do it right now just because I want to get us to lunch on time, but maybe this is an exercise, is to plug in an absorbance of 0.4 and then figure out what's phi t over phi I for that, for an absorbance of 0.4. And think about like, okay, you've got this light coming in, like what fraction of it are you actually able to measure if your absorbance is greater than 0.4? So it becomes a signal to noise issue. Like with increasing stuff, more and more and more stuff, you're not getting much more reduction in the light after a point. And so the ability of the spectrophotometer to discriminate this much versus this much is diminished above a certain optical density. Yeah. Okay. All right, so moving on to a third category of measurements, and these also kind of fit into this category of we want to know absorption, but there's scattering. So we're going to make a measurement and make informed assumptions about what the scattering did and try to correct for it. So, so the reflecting tube absorption and attenuation meters, the AC meters are kind of the biggest, kind of the ones that we typically will use. I think there might be some other manufacturers of these out there, but the ones that Wet Labs and now Sequoia Scientific makes are the ones everybody uses. So they have two parallel light paths. One of them is a reflective tube, and one of them is a non-reflective tube. So the reflective tube, the light travels down the path and it bounces around, it interacts with the walls, and then it hits a detector that's diffusing, right? So it's able to collect light from multiple directions. And then the non-reflective path, we're just looking at the light that's transmitted, we're not collecting any of that scattered light. So the reflecting tube is giving you something that's related to the absorption coefficient. The non-reflecting parallel tube is giving you the beam attenuation coefficient. And I guess Wayne's going to tell you about A plus B equals C tomorrow. Yeah. But beam attenuation is the sum of absorption and scattering. So the absorption measurement is measured in a cylinder with a reflective interior and a diffuser in front of the detector. And this schematic, which is from a different chapter of that IOCCG protocol document for particulate absorption measurement, so basically have a collimated unidirectional light source, and any light that's scattered through an angle smaller than about 42 degrees, and this has to do with there's a quartz wall and then an air gap, which results in that particular total internal reflection angle. Anything that's scattered through a 42 degree or less angle will make it over to the detector. But anything that's scattered at an angle larger than that will be lost, right? So we have to, and this works kind of because most scattering is in a forward direction, right? So it's only the larger angles, but there's less light scattered through those.
And that's what some of you saw. Most folks that did the refractive index station, you should have seen that total internal reflection.
Mm-hmm.
Yeah, the last station.
Yeah. So it's quartz and then air, kind of water quartz air gives you that property inside this reflective tube. So the schematic on the right hand side, the middle one, this is what we call the A tube, and the lower one is the C tube, right? A for absorption and C for beam attenuation. I don't know why. I don't know why B is scattering either, but yeah. But the difference here, so the C tube has non-reflecting walls, so anything that's scattered or absorbed is lost, and then there's a narrow field of view of the detector that should not be collecting most scattered light, but it is finite, it's not zero, and so there is a little tiny bit of forward scattered light, and Wayne will talk more about the effects of that. So those are the sort of general overview of these AC meters. Okay. And this is a photograph of one. You guys will be working with these in lab this afternoon, and then a schematic of how they're put together, basically showing a little more realistic depiction of the schematics that were shown on the previous slide. B equals C minus A. Okay, but in an AC meter, before you do any corrections of your data, absorption is overestimated because we have any light that's scattered through an angle steeper than 42 degrees is lost, right? And so that initially in the raw data gets reported as absorption, even though part of it is scattering. In fact, quite a lot of it can be scattering. And also because we have that non-finite detector acceptance angle on the beam attenuation side, you have some scattered light that's detected as transmitted, right? So scattering is underestimated and absorption is overestimated. So using these meters, we have to kind of figure out a way to correct for that based on what we know about our instruments, and in some cases, what we know about our water that we're measuring. And I said that, okay. So going forward in the next couple slides, I'm going to use A sub m, B sub m, C sub m to refer to the measured, like not what we've corrected, but just what comes out of the instrument, those spectra. Okay, so here is an example of what we're talking about. This is from a paper, Rudiger Rutgers in 2013. So here this is absorption. I don't know why. Oh, it's on the, for some reason, the axis is on the right-hand side here. But this is riverine water, so it's got a very high absorption coefficient and a high scattering coefficient. The solid black line is what we're going to call the true absorption spectrum, measured in an integrating sphere in suspension. So not even a filter pad, but putting the water in a cuvette and sticking it in an integrating sphere. So we can see that absorption isn't actually zero at 700 nanometers. That's interesting. File that away. And then they were using an AC meter, in this case an AC9, and the triangles here are the measured absorption that just came out. So as we see, absorption is overestimated by this instrument. What I'm showing you here, they've already corrected for the influence of temperature and salinity in the sample, and they've already removed pure water absorption. So we're just looking at the non-water absorption coefficient here. There's a few different methods to go about doing the correction. One is first to calculate the scattering. So I'm not showing you here the beam attenuation spectrum as measured, but if you take the difference between measured beam attenuation and measured absorption, you get the measured scattering, which is not the true scattering. We take the measured scattering, that calculated scattering, BM, and use it to estimate a correction to the absorption spectrum. The first method, we assume that the measured absorption in the near infrared at the reddest of the wavelengths available, in this case, 715, I think, we assume that that's zero. Because in much of the ocean, that's kind of true. You notice it's not in this place, right? But we can assume. Okay, so we assume that it's zero. And use that difference between the measured and zero to figure out a correction that needs to be removed from the entire spectrum. So this is the spectrally flat option. I don't think we're gonna do all the different corrections in the lab tomorrow. Yeah. Okay. So you can play around with the effects of these different correction methods. So in this case, you would remove that difference between measured and zero at 715 nanometers from all the other wavelengths. And in doing this, you get the black stars here. So this is the derived absorption spectrum. It's, not too bad at the blue wavelengths, but in the red wavelengths, we see that there's kind of a problem, right? It doesn't do a very good job of reproducing what was measured in the integrating sphere. So there's maybe something about that assumption that scattering is spectrally invariant that is problematic. Also with the assumption that absorption is zero at 715. Option 2 is to assume that that the spectral correction that needs to be applied to the absorption is equal to a constant proportion of the measured scattering. So rather than just taking a single value, we take a proportion of the scattering off. And so then that's the open circles here. It's actually not an improvement at all in this system. So this is in part due to the fact that absorption is non-zero, right, in this particular sample. So if you don't want to make that assumption, what else could you do? In this particular study, they took a whole bunch of samples and measured, like got the measured absorption at 715 and then compared it to paired measurements of the same samples in an integrating sphere and came up with an empirical relationship between absorption at 715 for real and absorption at 715 as measured, and then use that to do a correction. So that's another option. Mostly, I mean, in like I would say here, probably even in the Damascata estuary, it's probably safe to assume that absorption at 715 is close to zero. It's really when you start to get a lot of absorbing particles that are absorbing out into the infrared, often kind of sediments, things with a lot of iron oxides, et cetera, will do that.
Does that go sort of cleaner towards, or like less variance away from the line further away because there's less measurements with the higher absorbance?
I think in looking at this, if I look at the names of the places and where they're clustered on the graph, that most of the noise and things that are falling away from the line, it's all at the lower end. So one, we're getting into kind of noisier part of the data because it's close, it's lower, but also it's North Sea measurements and cultures. So phytoplankton cultures, we would really expect to not really have a lot of absorption at 715. And the North Sea is the most kind of offshore of, like, this is the Baltic Sea and a river, right? So these are more kind of scattering, turbid, mineral particle influenced environments. So I think this is on a log scale. So you're basically seeing kind of the shift from a pretty good relationship to, okay, we're starting to see like hard to measure low absorption coefficients and actually not that much influence of absorbing stuff in those environments. That would be my interpretation of the scatter around that line. Okay, yeah. Okay. And in their method, they also did a correction of beam attenuation for that underestimation of scattering due to the finite detector acceptance angle. And we'll have more on that tomorrow. So that's another step that was applied here.
I'll just say one more quick thing. You may be quite familiar with this, but maybe you may not be familiar looking at long log plots like this. And just make sure you think carefully each time you look at one, about what the scales are. The uncertainty inherent in the ACS is not huge, but when you're up in these high values of absorption. What are the highest there?
This tops out at 10. 10 to the 1.
So there almost certainly is an equivalent scatter around that, as we see them, like because of the way it's level, they can reveal patterns and obscure patterns.
Yeah. That's true. Actually, finding a linear version of that, creating one. Yeah.
So earlier, the absorption coefficient was near 1. And absorption here, we're saying is 0. Why, where does that, how do we connect the two, absorption coefficient and absorption?
Sorry, I don't, like, you mean like the absorption coefficient that we were looking at?
Like in the last lecture, near 715, if you look at that's what
so all of these, so the last slide says it, and I don't say it again on this one, but all the data that are shown here, they've already done temperature salinity corrections and they've already removed pure water. So that we are looking at the non-water absorption in all of these, right? So they subtract, and almost this afternoon we will do one set of measurements where you reference against air in the spectrophotometer, so you can actually see the water absorption. But in the AC meters and in the other set of measurements you do in the spectrophotometer, we're going to reference against water, which means we're never going to actually be looking at the water. It's a great reminder. You should always be thinking about the fact that water is absorbing like a hell of a lot of light in the red. And that's important when we're thinking about remote sensing for sure. But in the laboratory, in our IOP measurements, we often will reference against water. And so then we don't think about that.
Gotcha.
Yeah. Yeah. Good question. Okay. Did this. Okay. So I might leave you guys with a slide, or we can think about it later, but this is some data, a table, and then some figures from a really interesting experiment that was done in before 2021, but it was a multi-investigator method closure. It was not an experiment, really. It was an exercise that was carried out to see, and by closure, we mean we measure things by a lot of independent ways and they agree, which is really hard. And in this case, it's just in situ measurements, right? We start to like look for optical closure between in situ measurements and radiometric measurements. Like it gets even more complicated, right? But this was just a measurement closure exercise for in situ measurement of absorption. And many, I want to say Emmanuel was involved, Colin was involved. None of you guys were involved. Twardowski was.
I was associate editor of that paper.
Okay, so Ivana was involved in that way. But
Yeah.
yeah, so it was sort of carried out by a lot of it was like it's like the boomer generation of optical oceanographers. I don't think any of us are. But it was kind of it was neat to see kind of all the comparisons here. Kostakis was a postdoc that was associated with that exercise. But anyway, this is a paper that's worth reading if you want to sort of think about all of the caveats and all of the differences and all of the assumptions that go into all these different measurements. They had AC meters, they had integrating spheres, they had filter pad benchtop measurements, they had they were using radiance, irradiance, up and down measurements and determining the absorption coefficient inverted from that, so completely independent. They compared all of those and actually got pretty good results. And so it's kind of a useful, I think, for you guys at the end of today, and maybe you won't do this today, it might be like the weekend or something, but it's worth going. We don't have time right now, but it's worth actually looking through this table and looking at all the parameters and all of the terms and all of the plots that I'm showing here and thinking like, do I have the vocabulary that I need now if I were to go read this paper and understand it, right? And if you don't feel like you have the vocabulary at this point to go read this paper and understand it, then that's a great way to kind of identify more questions or more clarification that you might want to ask for from any of the instructors. It's kind of just sort of a mental to leave you with is, do you think this would make sense if you tried to read it? And, or close enough that you could approach it and start to kind of think about what they were doing. Okay. So I think that's all I've got. Oh, I've got a quick lab overview in our last 2 minutes. So this afternoon, we're all going to be in Mitchell classroom again, like we were yesterday. And we've got 3 hours of activities, and we'll divide the class in half. And you'll spend 90 minutes on one activity, one set of activities, and the other class will do the other one. And then at 90 minutes, we'll take a break and then switch. So group one will be doing, half of group one will be doing like a simple, it's like using food coloring and light sensors and flashlights to sort of empirically replicate Beer's law in a little tank. And then the other half of the group will be working on a benchtop spectrophotometer, making measurements to look at the effect of temperature and salinity and path length in measurements of pure water and natural water, and just how to operate the spectrophotometer. And then group two will be divided in 3, and each group will have one instructor and one AC meter that you will hang out with the whole time, and you're going to learn how to operate them, clean them, get the data from them, do some initial processing of that data, and then you're going to make measurements on a couple of samples. And together, and then you'll switch. No group is going to measure everything that needs to be measured to do the analysis for this particular lab. Each group's going to just measure a couple of things. So you're all going to have to get together and put all your data together and then use it to actually make inferences about what you've done. So there's a bunch of questions that will have you address with your data, and that will be the start of our class time tomorrow. So the things we want you to think about are how the absorption spectrum of purified water varies with temperature. You know what you ought to see, but you're going to measure it yourselves. And we can talk about how that looks compared to your expectations. And the same thing as a function of salinity. So you'll have some water samples, some pure water samples with salt added and not. And then the Beer's Law demonstration, whether that follows what you expect. The impact of geometric path length, meaning path length the light goes through, on the measured absorbance and the absorption coefficient. And then we'll be measuring water from the estuary out here and from Damascotta Lake, which is the freshwater body at the top of the watershed here. So you'll have two different natural water samples, and you can look at CDOM spectral slope basically along this watershed. And so, like I said, you're going to have to figure out how you want to combine and then divide and conquer to carry out the analysis for tomorrow. So that's the big overview. And once we get in Mitchell, it's going to be all like loud and people everywhere doing things. Ivana.
The processing of the ACS data, put something on the screen there to make the code, or?
Yeah, so we can do, I think option one would be just for when people are in the AC meter groups to actually just go through that in small groups if there's time. And I think we should play that by ear. And if there's not time, then maybe we bring everybody together at the end and Alexander or Patrick can get the code up on the big screen in there and we can just go through it.
Yeah, I'll just say quickly, we have this in Python and MATLAB. Should be identical. And we can, maybe you don't know chalkboard, write the steps.
Mm-hmm.
You should play with these functions and then very well commented.
Yeah.
We won't have everything for you in both Python.
Okay. All right. Let us go eat.